This is Algebra 2, the second half of Section 1.4, where our learning target is students will be able to solve linear systems of equations by graphing. Last video, we talked about the fact that where two systems of equations intersect will be the solution to that system of equations. So let's go ahead and actually get to some graphing, right? Let's make sure we remember how to graph some things. So here, we're trying to find where these two lines intersect with one another. I have 5x minus 2y equals negative 10 and 2x minus 4y equals 12. These are both in what we call standard form. Now, when you graph standard form, you have a couple of options. We're going to go through a couple of different examples. The first, we're going to use what's called the intercept method. We are going to find the x and y intercepts for each of these equations and use those to graph them on the coordinate plane over here. So let's start with 5x minus 2y equals negative 10. If I want to find the x-intercept, and this is from our very first section that we did, I need to plug in y equals 0. So let's go ahead and do that. I get that my x-intercept is going to be at the coordinate point negative 2, 0. Now for my y-intercept, I do a similar strategy, but this time I'm going to be plugging in x equals 0. So I get 0, 5 is my y-intercept. Now I have enough points that I can go ahead and graph the line. You really only need 2 points to graph a line. You might want a ruler for this example, for this section here, because it's really important that we fill up the entire coordinate plane. I don't know where the other line is going to intersect, so I've got to make sure that I have the full coordinate plane filled out. Let's do the same thing with our other equation, 6x minus 4y equals 12. I encourage you to pause the video and try finding the x and y intercepts on your own. For my x-intercept, right, I'm going to plug in y is equal to 0. So I get 2x minus 4 times 0 equals 12. So I get the point 6, 0. Sedlick, you left off not enough space. We'll say it's out there. My y-intercept, I'm going to plug in x is equal to 0. Get 0, negative 3. So let's see what we got. Once I graph those, I'm going to figure out where they intersect. My solution is the point at which they intersect, which is at the coordinate point negative 4, negative 5, which is ultimately what I was going for. Let's try another example. In this next example, I have equations that are, the second one is almost in standard form, but that negative 2, that should have been a positive 2 out front. But I have similar lines. They're not always as easy to necessarily graph. In this example here, I want us to take a different approach. I want us to put both of these equations into the y equals mx plus b format. I think sometimes students are a little bit more comfortable with that format, so I want us to give that a try so that you have alternative ways of working through these problems on the homework assignment. So let's look at our first example. To solve for y, I'm going to subtract 4x. I get negative 3y is equal to negative 4x minus 3. Notice how I put the negative 4x first because I'm trying to get it in this form, right? I want the x part up front. Then I need to divide everything, and I mean everything, by a negative 3. I get y equals a negative divided by a negative is a positive. A negative 3 divided by another negative 3 is a positive 1. So I have 4/3 x plus 1. I'm going to go ahead and graph that by realizing my y-intercept is at 1 and my slope is up 4 to the right 3. Or you can also think of it as down 4 to the left 3. But now at least I have enough points that I can go ahead and graph that line. Now let's look at our second equation. I have negative 2x plus 3y equals 9. I'm going to add 2x to both sides. Divide by 3. Remember, I must divide everything by 3. 2/3 x plus 3. My y-intercept is 3, and my slope is up 2 to the right 3. Oh, I think I already see where they intersect. Go ahead and plot that line, and then find your intersection point, right? My intersection point is up here. It's at the coordinate point 3, 5. Let's ask ourselves some questions. Is the solution to a system of equations always a single point? No, not necessarily, right? There's a couple of options where we don't always get a single point. We could have lines that don't touch. That usually means, right, that they are parallel. We also could have lines that are overlapping. Basically, if you get the same line, then they are overlapping right on top of each other, right? If I've got this line, and then I graph the next line, and it is the exact same line, and it is right on top, then no. There is not a single point solution. Can a system have no solution? Yes. Parallel lines. Does graphing always provide an exact pointer solution? Unfortunately, that's not the case, right? If I have a solution and it happens to be in between the grid lines on my coordinate plane, it's hard for me to know what that value is without using technology. And even if I use my calculator, which we're going to get to as we go through this section, it's still something that I may have to round, which is unacceptable, right? We're trying to be as exact as we possibly can. Within a system of equations, we have a classifying system, right? What we do is we not only tell you what the solution is, but then we label them as either consistent independent, consistent dependent, or inconsistent. A consistent system has at least one solution. And from there, I have two options. A consistent independent system has exactly one solution. That's the ones that we've seen so far, where they are exactly one coordinate point where they meet. Whereas a consistent dependent system is infinitely many solutions. An inconsistent system means I have no solution. Up here, this is when I have parallel lines. And down here with infinitely, that's where I have the same lines. So let's go ahead and get to some of these examples, right? We've done the exactly one solution, the consistent independent. Let's look at a consistent dependent and an inconsistent system. For this one, right, I want to be able to graph this. And thankfully, I've got y equals negative 3x plus 1. Finally, we have an example where it's already in mx plus b format. So I'm going to go ahead and plot my y-intercept and then use my slope of a negative 3. Remember, that's down 3 to the right 1. Or up 3 and to the left 1. Remember, I'm trying to graph this. Oh, that was not a very straight line. See if I can do a better job drawing this line. Not much better. All right, third time's a charm. There we go. Now our next one is unfortunately not in the nice y equals mx plus b form. So let's go ahead and practice how we solve for y. Practice some of our algebra skills. I'm going to subtract 6x. I get 2y equals negative 6x plus 8 divided by 2. I get y equals, remember you have to divide everything, negative 3x plus 4. My y-intercept is up here at 4. Oh, I think I see a little pattern here. Right, these guys are never going to be able to touch. The solution is that there is no solution. No solution. Because we have parallel lines. I classify it by using kind of my little chart up here to determine that my classification is inconsistent. Let's try another one. I'm going to go ahead and graph these. Now, I would love it if they're in y equals mx plus b. They are not, but let's go ahead and convert them. Again, some good algebra practice here. I'm going to add x. I must divide both of these, and remember there's a 1x there. So I'm going to write this as y equals 1/3 x plus 2. I'm going to go ahead and plot that. Up 1, 2, 3, down, up 3. There we go. Let's do the same thing with the other equation. Remember to divide both of these by negative 9. Oh, negative 3 divided by negative 9, that simplifies down to a 1/3. Negative 18 divided by negative 9, well, look at that. We have the exact same equation of a line. These two lines are overlapping, right? They are the exact same line. But when we first looked at these equations, that didn't stand out right to us, right? That wasn't evident right away that these were the exact same lines. My solution is that I have infinitely many solutions. Because they are the same line. And I classify that, let me go back to my classification, as consistent dependent. So that's exactly what I write down, is consistent dependent. And if on your homework you want to just write down CD as a shortcut, I am totally fine with that. So let's go ahead and summarize some of the information that we've learned so far. With exactly one solution, they meet at a single point. We classify that as consistent independent, and the big thing that it can be our shortcut is that they have different slopes. For an infinite system, there are many points, right? There's an infinitely number of points where they meet. We classify that as consistent dependent, and it's the exact same equation. Whereas in our last example, that's no solution. There are no points where they intersect. It is called inconsistent, and we end up with the exact same slope, but different y-intercept. Let's just use the fact that I need to figure out what the y equals mx plus b format is for each of the equations below. Once I see the slopes and the y-intercepts, I don't necessarily have to graph them in order to classify them. So you'll notice that example 7 is simply just asking you to classify the following lines without graphing. Meaning, if I put all of these equations into y equals mx plus b, I should be able to just look at the m and the b and figure out their classifications. Is it consistent independent, consistent dependent, or inconsistent? I encourage you to pause the video and take the time to convert all of these into y equals mx plus b and try classifying them on your own. For our first example here, when I convert them, I get y equals 3 halves x and y equals 3 halves x minus 3 halves. What I notice here is they have the same slope, but a different y-intercept, right? This y-intercept is 0, this one is negative 3 halves, so therefore I can classify it as inconsistent. In this example, this one was the easiest one, right? Negative 4x plus 3, negative 4x plus 3. I notice this is the exact same equation, so I classify that as consistent dependent. And over here, if I rewrite those, I get y equals negative 3 halves x and y equals negative 5x plus 6. I have completely different slopes. So with different slopes, I can classify that as consistent and independent. Let's go ahead and try out how to use a graphing calculator. And if you don't have a graphing calculator, I encourage you to get one, especially if you're going to keep taking math classes after Algebra 2. If you're going to go to college, a graphing calculator can come in handy, and it is allowed to be used on the ACT exam. So go ahead and take out a graphing calculator, or you can download software for either if you're a PC user, you can download a graphing calculator to your PC, or if you're an iPad user, there is a Calc84 app that is on there that you can follow along with. What we're going to do is we're going to have the calculator figure out the intersection point for these two lines without having to graph it ourselves. In the world of Algebra 2, I always encourage you to use your resources, and a big resource is that calculator. So let me open up mine. When you open up your graphing calculator, go to the y equals menu. Within here, we'll want to type in our first equation, x plus 1. And you'll notice my x is right next to my alpha button. In my second equation, I want to put in the next one, which is 2x plus 4. Once I hit graph, hopefully I'll see those two on my axis there. And I see that they intersect. Now I want the calculator to find that intersection point for me. So I hit second trace to go to my calculate menu, choose number 5, and you'll notice your calculator is not smart enough to know if you've entered 2 equations or 100 equations. So you have to tell it which curve to evaluate, meaning which line. Well, I do want to include x plus 1, and it's asking, is that the first equation you want me to analyze? Just hit enter. Then it will ask, is 2x plus 4 the second line? Yes, it is. Just hit enter. And then last but not least, your calculator wants you to even guess the answer for it. Use the left and right arrow keys to move your cursor so that it's over the intersection point as close as possible. Hit enter one more time, and you'll notice that our solution is at the intersection point -3, -2. So let's go back here and write that our solution is at -3, -2. And if I were to classify this, I would classify it as consistent and independent since we have one solution. Let's look at an ACT question, right? A word problem type question. Those always come up on the ACT, and we're going to use our calculator to solve this for us. You're working hard to make some extra cash for spending money. You worked 14 hours last week at your two jobs combined and earned a total of $122 before taxes. Your job at Build-A-Bear pays $10.50 an hour, and your job at Hy-Vee pays $7 an hour. Oh, you should ask for a raise. How many hours did you work at each job? So in order to solve this, I need two equations. I need to have a system of equations. Go ahead and pause the video and try to come up with those equations on your own. I'm going to make x equal to the number of hours at Build-A-Bear and y my number of hours at Hy-Vee. It's always important to identify what your variables mean. Your first equation is going to be the money equation. 10.5x plus 7y equals 122. The other equation, I haven't used this 14 hours, is x plus y equals 14. So I want to go ahead and plug these into my calculator to be able to solve for me. But you'll notice when we use the calculator, they have to be in y equals format. So let's convert both of these over to y equals. Well, my second equation is pretty easy. I get y equals negative x plus 14. I just had to subtract the x. Now my second equation, that's a little bit more challenging. So let's take our time. I'm going to subtract 10.5 from both sides. So I get negative 10.5x plus 22, and that's equal to my 7y. I then am going to divide everything by 7. I get y equals negative 10.5 over 7x, and I know this is ugly, plus 122 over 7. So that is my second equation. And you know what? Your calculator does not care if you have an ugly fraction, if you have a decimal in your fraction, it can still handle it. So let's go ahead and make sure we know how to type these into the calculator and solve for us again. I go back to my y equals menu and I'm going to clear out these answers. Let's go ahead and type each one of these in. Your negative button is down here. Don't use the minus button. Negative x plus 14 was my first equation. And then for my second equation, I need to make sure I put the fractions in parentheses. Negative 10.5 divided by 7, x plus 122 divided by 7. Go ahead and take a look at the way that we've put that into the calculator to make sure that you did the same. I then graph it, and I see up here in quadrant 1, they are intersecting. So I go to second trace, I want to pick intersect, and then I hit enter, enter, enter. And it's going to tell me that my intersection point right up here is 6.85, or let's say 6.86, we'll round correctly, and 7.14. So that tells me that the number of hours that I worked at Build-A-Bear, that was 6.86. And the number of hours I worked at Hy-Vee was 7.14. And those are the solutions to your system. You have a couple of pages of notes that outline how to do all of this on your calculator. I know they can be overwhelming to read. Just know we went through an example, 2 examples, on how to do it on your calculator. You should be prepared to go ahead and do the 1.4 homework.